you have witnessed the awesome power of Gauss's law to calculate an electric field. We did it for a point charge. We got Coulomb's law. Let's do it again for another geometry. Let's do it for a line of charge. This is another fundamental geometry we want to think about. So let's see. Let's have a thin little line of charge like this. Okay. You characterize the charge on a line with lambda. So it's got lambda coulombs per meter. We want to use Gauss's law. We want to say the integral of E dot dA over some surface is equal to the charge enclosed over epsilon naught, and we want to find E. And we talked about before, we can't just solve this for E. First, we have to pick a surface that uses symmetry that allows us to get rid of the dot product and maybe get the E outside the integral. So that's the game we're playing. So let's think, what surface would do that? Well, as you move away from the rod, the E field is going to point out. So remember, we calculated the E field for a point kind of like that along the center of the rod. Right? So you could say, okay, I'm going to draw a surface like that, but then the same thing would be true down here. The E field would point out, radially out, for this point down here. So you could draw it down here as well. Okay? So you could say, I can make a cylindrical surface where the E field always points out. The dAs of the cylindrical surface always point out. Therefore, that's a good surface. And then you might worry, oh, it's going to have these sides. What about that part of the surface? Well, that's okay. Oops. Because if the E field is pointing out, that'll always be perpendicular. A would be this way, E would be out. So those might give you 0. So let's just draw it, and then we'll think about it. Like that. So it's a cylindrical surface going around the line of charge. Now, I have made a mistake. Trust me, it was on purpose. But let's think about symmetry here. Symmetry told us that at this point, the E field only pointed up. And at this point, it only points down. We calculated that before. But that was only on the center, right? Remember, we had to be symmetric around this axis. We had to have a rod of length L, and we had to put this on the origin, and this was L over 2, and this was minus L over 2. That was the way we had the symmetry. If you went over here, you broke the symmetry. E would not actually be in the radial direction. It would actually have some angle with respect to the surface. So that's no good for using Gauss's law. It'll work. I mean, you could do it, but that's hard vector calculus. We want these easy symmetric cases. So actually, we can't do Gauss's law in physics 1 for a short rod. We actually can only do it for an infinite line of charge, or a rod, a line. We can't do it for a finite line of charge. We actually only do it for an infinite line of charge. Goes to infinity there, goes to infinity there. Okay? Because only if it's infinitely long are all these points basically equivalent. Wherever you go, there's just as much charge on that side as there is on that side. There's a symmetry. There's no reason you would have a component this way or this way. There's just no reason to, because there's always the same amount of rod on each side. So if you do that, then sure enough, E will actually be out, radially out, all along the cylinder. And what I'm not drawing is on this front face, E will stick out. Right? So everywhere you go, E and dA are going to be parallel on that surface. So that's the key. Actually, you have to consider the symmetry very carefully. You can only do this for an infinite rod, not for a finite rod, the way we're going to do it. Okay? Okay, so we have to then deal with this integral. So the way you do a closed surface integral on a sort of a complicated surface like this is you just break it up into pieces. Okay? So this cylinder has basically 3 surfaces to deal with. The end cap here is 1. We'll call the side here 2. And we'll call that backside 3. Okay? So this 2 is really a rectangle if you unravel the can, and the 2 ends are circles. So the way you do it is you take this closed surface integral and you break it up into 3 integrals. I could write them as 1 of E dot dA plus 2 of E dot dA plus 3 of E dot dA. And that has to equal Q enclosed over epsilon naught. So they're not closed integrals anymore because they're not closed surfaces anymore. They are pieces that when they come together, they make a closed surface. Okay? So let's look at each surface. Well, we know for surface 1 that the E field, no matter where you go, always points radially out. Here up, here down, out of the board, etc. And we know that the dA always points to the left because that's the closed surface. We want the A's to come out. So basically dA and E are perpendicular. Okay? So E is perpendicular to dA. So that one is 0. Okay? 3, let's jump over to 3, will be the same thing. E will always point up. A, dA will always point out. So this one is also going to be 0. E is always going to be perpendicular to dA. So that one's 0. Okay. For the middle one, let's think about it. E and dA are always in the same direction. All right. Up here, down here, out of the board here, into the board on the back. So that gets rid of the dot product. We can just do it without writing so many steps. E times dA, just magnitudes. And then E is also constant. Right? According to symmetry, there's no reason the E would be different here than out here going around, because those are all equivalent points. You're always the same distance away from the cylinder. Right? It doesn't really matter where you are. So now E has come out of the integral. Oh, well, so I'll write it down here. So E is parallel to dA, and E is constant, are the two things we learned from symmetry. So E comes out of the integral, and then it's just the integral of dA. And what is that? That's just the area. So we need the area of this Gaussian surface. So that brings up another point, is you have to give your Gaussian surfaces dimensions. We have to actually say it's a Gaussian surface of length L. Okay? And it's a Gaussian surface of radius R. A lot of times the dimension will cancel when you're done, but for the intermediate steps, you do have to give it a dimension. Okay? So if we imagine unraveling this into a rectangle, it's going to be L along one direction, L, and its length, after you unravel it, is really just going to be the circumference. So that's 2 pi r. So EL 2 pi r. So that is the contribution to the sides of the vector flux coming out, and you have 0 from the ends. So there's another case where we did vector calculus. If you really understand what it means, you know which parts are 0 and you know how to get the other parts when everything is nice and symmetric. Okay? So we have E L 2 pi r equals, and now we need the charge enclosed. Well, we know the charge enclosed. We know it's lambda charge per unit length, and we know the length. So that's just lambda L over epsilon naught. Okay. So we gave our Gaussian surface 2 dimensions, a length and a radius, and the length is going to cancel. See, we have E L 2 pi r equals lambda L over epsilon naught. L's go away. And we can solve for E. So E, the E field magnitude, is simply lambda over 2 pi epsilon naught r. Right? That's the magnitude of the E field. We could give it a unit vector if we wanted to. It's the symmetry that told us the direction. From the symmetry, we know the direction is out in the radial direction. So if we wanted to, we could make it an r hat, or whatever coordinate system you set up. But the key is we found the magnitude. The other key is we found the magnitude of the field everywhere. Right? So we made our Gaussian surface. The length, turns out, is something that cancels and goes away. But the radius stays, because the E field does actually depend on the radius. So it's another case where Gauss's law didn't just tell you the E field on this one specific surface. Because we chose the Gaussian surface well, it tells us the E field everywhere in space. Because everything we did would be true for any radius. So that's why the radius stayed. And you can see that the E field then, near a line of charge, drops off as 1 over r. Not as fast as from a point charge. There it drops as 1 over r squared. From a line of charge, it drops as 1 over r. We learned all that from Gauss's law.